Hello dear students, my name is Tidzislaw and I will be doing this lecture in medical physics. So medical physics and physics in general. Why the physics? The most asked question among you. And there are several answers on this, and maybe this is one answer from a fun side of uh, yeah, but you know that in every joke there's a little bit of truth in it. Yeah, knowledge. This is what we're gonna gain in the university. This is what we already gained in high school and before that. But turns out that knowing facts it's not enough, and we have to train ourselves to put these facts together. We have to look on the processes, to describe the process, how they work, describe these processes with a known knowledge. And this is what the physics is here for, to train us. And putting all of this together, knowledge and logics, this allows us to define the environment where we live, define the world around us. One of my favorite answers to this question, why physics, is actually physics gives a job to medics. Yeah, you as a future medics, you have the job because of the physics. And the related answer here would be every trauma uh, is caused because of some kind of physics fundamental behind of it. And the other part of this answer is actually within your job, you will work because of the physics. From instrument point of view, think about that. All instruments and all medicine equipment nowadays, this contemporary or modern medicine equipment works because of the physics. And this physics allows us to develop. There's also this part where it's good to know some basics how the nature work, what we describe as a physics, to avoid of pseudoscience, to avoid being a stupidest person in the room or in the internet by just writing some comments in Facebook or whatever. You think about that. So yeah, physics, it's not only about the putting knowledge together to describe the processes. It's more than that. Are you afraid of physics? I could be in your shoes, but you should not be afraid. You should find the most interesting aspects of this course, of most interesting aspects of physics in your profession. Nevertheless, there are, let's say, four entities or four things which defines this physical reality, and engineering, logics, mathematics, and physics. What would be the series, or what would be the first fundamental part from here? And if I think about that, I think logics is beginning of everything. Yes, no, true, false, and based on that we can build mathematics, logics. This is a kind of abstract part of this. But what's left is physics and engineering. How do you think what's next? Well, I think it is actually physics. Physics which can be complicated sometimes, um, sometimes simplified. There are a lot of models in the physics. Physics actually consists of models. Conceptual models or mathematical models, doesn't matter, as long as there are models. This part is super interesting for most of the people in the world. But that's not all. Physics is not the end of everything. It's actually the point where we can, of course, make new things. We can build new things. We can engineer something new. And yeah, that would be the series of these order of these four entities, which leads to from abstract part to physical reality part. Yeah, and the question where the border between abstraction and reality is somewhere between mathematics, physics. There's no strict border. It depends on point of view, and this is rather philosophy than physics at this moment. But let's step one step ahead and one step forward and think about physics, especially medical physics. Medical physics in our course going to be applied physics. We will look on concepts. We will look on how stuff works. We will look on how some particular methods work. And we will try to pull most interesting aspects on out of this topic, medical physics. Nevertheless, there will be a little bit of math behind of everything. Do not afraid. Yeah, this not gonna hurt. Applied physics, by definition, is the bridge. No, well, definition is a tough word to say here, but yeah, applied physics is the bridge between physics and engineering. This is the moment when we can think about to construct things based on concepts, and then engineers are taking this over and actually building that device to help our lives better. Some examples of medical physics would be nice to see here, and well, how about mechanics? Mechanics and prosthetics? Why not? Yeah, biomechanics, prosthetics in a modern day, contemporary medicine is really related with the electronics and automatization, how to control these prosthetics with not only mechanical aspects, but also with the help of brain. Let's think about one step ahead. This is pure engineering work, but it works because of physics concepts. And a super simple example here is how to pull out teeth. Dentistry, yeah, dentistry example with a momentum enough, it's possible to get rid of tooth. Under the mechanics, we can find particular type of motion, rotational motion. How about that? Okay, this maybe is a not, well, nice example here, but why not? Cutting everywhere where we need some rotational instruments. Maybe dentistry is a little bit better example because, well, we have dental drills, and there's another way how to work with the tooth. Yeah. And the rotating things have torque in them. And this is what torque is doing, breaking things apart or pulling teeth out. Let's watch that again. And tooth got out of his mouth. Yeah, dental drill. Let's go on, and acoustics and vibrations and oscillations as the physical topic under medical physics could be seen in, well, of course, any kind of sonographical methods, sonography. Sonography, but a little bit more simpler example is stethoscopes, phone endoscopes, things what you will very often use to hear different sounds produced by human body. Electricity, let's go modern. Electricity as the therapy. Um, Electricity as the therapy, there's plenty of therapeutic methods what can be done with electricity, stimulating methods. We can stimulate brains, we can stimulate muscles, we can stimulate a heart, actually defibrillator. And the most famous defibrillator is nothing else, just an electrical power, not entirely supply, but it is supplying electricity when the defibrillation is happening. And the other part of electricity is diagnostics. Our body is producing biological signals, which involves electric characteristics, and these signals can be obtained, and most commonly we know it's electrocardiography method. Besides of electrocardiography method, where we are recording the heartbeat, how good the heart is, we can measure also the brain activity, electroencephalography, brain chemical signals inside of the neurons, because of this electrochemical properties. They are detectable. This besides of electroencephalography, there's more. There's electromyography, muscles, the detection of how good the muscles work. Electrooculography, specific technique where the eye muscles are diagnosed. And there are more than that as well. Okay, what else we have here? Electricity and electromagnetism, those are related topics, of course. And electromagnetism mostly relates with electromagnetic radiation. So electromagnetism or electromagnetic radiation, what lies under that one? How about X-rays? So we see definitely the X-ray image of the jaw, and that's one of the examples. We can think about electromagnetic radiation in full, let's say, full spectrum. And besides of the X-rays, we also know there's an infrared spectrum, and radio waves, and ultraviolet, and gamma rays, and visible light, and microwaves. Well, here we see, who knows, artificially made or real infrared image of, well, you know what. If we focus on magnets, then magnetism can be found as another specific separate topic, medical physics. And how about something X-ray similar looking image? But this is not X-ray. This is actually magnetic resonance imaging, MRI, magnetic resonance imaging technique. Another way how to visualize, how to detect, or how to see parts of the body layer by layer. Magnetism, not entirely magnets, but magnetism. And who would know that this is possible because of water has some magnetic properties? Yeah, a little bit about this you will learn in this course, and more about that in the radiology course. But besides of something complicated like that, we also have a super simple approach where magnets can be used, and here it is, keeping the prosthetics in their place. Because, well, accidents about losing teeth also could happen here. Well, Besides of that, another electromagnetic related electromagnetic electromagnetic radiation related topic, laser, specific type of uh, light here where it can be used. How about using laser light as the scalpel? And there's another dentistry related procedure. Why not? Cutting part of the gum from the gum. So before there's a lot of gum covering the teeth, but after this procedure, the smile and the teeth looks significantly better. And in the medicine, ophthalmology related topic would be LASIK. LASIK is the procedure where the frontal part of the cornea is reshaped, made more flattened or more curved, and with this, the dioptries could be reduced or eliminated for the eye completely. Complicated technique, but not long procedure using a powerful laser. So rest of the presentation will look on the fundamental physics, fundamental forces, a little bit of biophysics, a little bit of liquid dynamics, and let's move on. The ultimate question of life, universe, and everything is complicated. Well, one of the questions would be what holds everything together? And by everything, I mean everything. Yeah. What holds atoms together? Or what holds galaxies together? Another question could be what makes us to actually live? What is life? Would be another question here. I am not sure that we will be able to answer to these philosophical questions, but we still could do that. We still can ask these questions. Another one, where is the end of the universe? Or what is the smallest thing? For that, I really encourage you to check out this presentation, The Scale of the Universe, and check it out. It's dynamic, it's interactive, and you can find it in the presentation outlines. But we will move on, and we will try to look on this question, what holds everything together, and the answer is 4 forces. 4 forces instead of horses. One of those is gravity, another one is electromagnetic interaction. Then we have strong nuclear force or strong nuclear interaction, and another nuclear force or weak nuclear force, weak nuclear interaction. All of these 4 fundamental interactions are in the base of life. We all are familiar with gravity, of course. Well, maybe we don't think a lot about that in every day, but this is important if we want to sell something which has certain weight. Well, if it weighs more, of course, we want to earn more profit. But this is a little bit off topic here. We will go through all of those 4 forces eventually today. And let's start with gravity. And the fundamental idea of gravity is that everything which has two mass, everything which has mass, everything which has mass will attract to something which also has mass. Or crazy. If there are 2 objects and both have mass, there is a interaction between those 2 objects. Of course, Sun and Earth. Yeah, we are in the orbit around the Sun with the Earth. And Yeah, there's a gravitational interaction. Even more familiar idea. You have a mass and Earth have mass. And well, these two things or two objects which have mass, you and Earth, you are attracting each other. It is not only that Earth is attracting you. Yeah, you are attracting Earth as well, and equally strong, by the way. So if we look on the schematics, maybe you are already familiar with this, but we need two objects, green object, yellowish object, and let's say that these objects have mass. Mass 1 and mass 2 are representing those objects, and there's also certain distance between those two objects. Let's note this distance with a symbol d here. And this interaction, which we mostly recognize as the force, can be written in this universal gravitational form of universal gravitational law. We have mass 1 in the green color. We have mass 2 in the, well, purple color. And we have distance among these two masses. And then we also have something which is denoted as G, universal constant, gravity constant. Interesting moment here is that distance matters significantly, and if you increase distance twice, the force will be changed, decreasing 4 times, twice squared times. Even more, if distance is tripled, then the force is changing 3 in the power of 2, 9 times. Okay, does it matter if we think about how strongly you hold together with somebody who is living far, far away? Well, I mean, if you have a girlfriend left in your home country, there's definitely some kind of force between you and your girlfriend, well, or boyfriend. It is gender independent part here. But the idea is, yeah, it, I think I will have to cut this out. Anyways, longer distance gonna be, weaker force will exist between these two objects or subjects. We have to remember that force is measured in newtons, and everything in the equation, left side and right side, should be newtons. And this is the story about the gravity universal constant, universal gravity constant. This universal gravity constant is actually doing two things. This universal gravity constant is actually giving us the proper units. So if the right side has gravity constant and left side has only force, left side has newtons. So let's write some notes at this moment. Okay. Let me annotate this part. Yeah, so here we have newtons, and here we have, well, mass is in kilograms, another kilograms. This is distance. Distance we measure in meters. Distance squared is square meters. So this becomes kilograms squared over square meters squared. But what we need is we need newtons. So G, universal constant here, should have, and let's mark it like this. So these are units. Units and symbols in the formula should not be messed up. So this is kilograms, and square meters, and this is G. So G has to be something which eliminates kilograms. It has to be something which eliminates square meters, and it has to have newtons in it. So this part here is the unit for universal constant, universal gravity constant. So that's the one thing what this universal gravity constant is doing. It is fixing the units. The other part, what this is doing, is what constants usually do. Constants are scaling the result. Scale. Scaling, not the sailing, but scaling. Constant is fixing the units and scaling the result to get newtons here. So that's about the formula here. And we have the first problem. If my mass is roughly 80 kilo and student is sitting 20 meters aside from me and weights less, so probably some tinier student, I know that because of the gravitational force, we are attracted to each other. I highly doubt that I will observe any particular motion because of some other forces are involved in this story, like a friction force, which is not letting me to slide towards the student. But still, the force exists. So the question is, let me clear the mouse. How strong this force is between me and that another student. So I know that I have to use this formula. Now I know what G is. That G is this constant which is making the units correct and also scaling the results here. And if I'm plugging the number in the result, G 6,67 times 10 in the power of 11 times my mass times student's mass divided by a distance, we are sitting apart and we get our result. Solved 8,67 times 10 in the power of minus 10 newtons. And I know that the force always can be related with the feeling how much something weighs. 1 Newton, because of weight, feels like holding 100 grams of anything. So 10 newtons roughly feels like a 1 kilogram. Take something in your hand which weighs 10 newtons means that take something which has a mass of 1 kilogram. 1 kilogram, roughly 10 newtons. The result here is, wow, with a lot of zeros before the significant number, 10 zeros, times 10 in the power of negative 10. That means that it's, by recalculating it, it's roughly 0.8 nanograms, if I'm not mistaken, zeros here. That small attraction force actually we are having here. Have you ever thought about how much 1 gram weighs? If you have, then at this moment you could think about how much 1 milligram weighs, or let's go even more smaller scale, how much 1 microgram weighs. And only here, after microgram, we can find nanograms. So that's crazy. Let's move on and clear the drawings. And let's do some conclusions. Gravity. If the Earth is attracting me by the law of gravity, I already said that the Earth, I am attracting the Earth too because of particular Newton's law. And how strong? Equally strong. And now let's pick particularly 1 kilogram heavy object on the surface of the Earth, and let's think with how much force the Earth is attracting this cerebral cortex. And what we have to remember is, well, previous formula. We also have to understand the the distance between Earth and the brain. But at this moment, it's important to look at the distance from the central point. Where is the center of the Earth, and where is the center of the cerebral cortex? This is the distance we have to take in account. So if I know that Earth's diameter is roughly 12,742 kilometers, I need to use the radius, which is half of that. I also need to know how heavy the Earth is, and that's its estimated mass for the Earth in kilograms. And this is it. This is all I need to know, and just by looking on the equation, I see something familiar for me, and this is G, constant. This is mass of the cerebral cortex. This is mass of the Earth, and this is radius of the Earth in, by the way, meters. Yeah, so mass 1, mass 2, distance, radius. I will write it so you're not missing this out. And radius is obviously squared. Yeah. And when we do the calculations a little bit more, then plugging in the numbers, solving the numbers. This is an interesting moment where you can see the math with the numbers having powers here. 10 in the power of negative 11, positive 24, minus 6 times 2, so that's minus 12, can be solved out, and the final result is 9.81. Well, this sounds familiar. With that much force, Earth is attracting 1 kilogram heavy object. So yeah, this is interesting because if I would have a twice heavier object, if I have 2 kilos, how much force I'm gonna have? Well, twice more, twice times 9.81 newtons. And this is what you know from previous high school education, probably, that you know that the weight is possible to calculate when you take the mass and multiply it by so-called 9.81 coefficient, which in this moment also is how strong 1 kilogram is attracted. In this moment, I will write small g, mass mg. Yeah, force or gravitational force equals m times g. So this is a formula for weight. Okay, that's it. Let's move on. Weight and mass. Mass is a measure of inertia, how much the body resists to accelerate or change its velocity. So think about this image here. If the truck is slowing down to avoiding accident, and if the car is having a lot of cargo in the terms of mass, and this cargo is unstable, well, another type of accidents could happen. But the weight is it is a force of the gravity on the object. Think about that on the Earth, 1 kilogram is attracted approximately with this 9.81 newtons. As we already spoke, 2 kilograms is attracted twice more, but on the Moon, it is not gonna be the same number. Moon is smaller, Moon has less mass, so weight on the Moon is smaller, but mass stays the same. If you go to the Moon, you lose weight, but you don't lose mass. And here is the formula I already wrote, as well as some explanation of what I already said. Mass 120 kilograms on the Earth is the same mass on the Moon. but attraction force is way smaller. Does it mean that you can jump higher on the moon? Think about that. Inertia. As I already said, it's a measure of objects to resist changing velocity. Webster Dictionary tries to say something even more complicated, property of matter by which it continues in its existing state. Okay, this is something about being in a motion with a constant velocity or staying stable unless that state is changed. So yeah, changing velocity is the key moment of the inertia. I think that the previous slide having this simple word explanation is a little bit better for understanding what inertia of the object is. Resistance to change the velocity. And it turns out that inertia of the head is a reason for particular type of trauma, whiplash. So what you see here in this video is a water skiing, and look once more on the head. What happens with the head? Girl is holding the head and her head stays as but the hands are pulled by the rope, and this could be pretty deadly. And this is what we see here in the schematics. Sudden change of speed, yeah? And because of head has its mass, and more mass will mean more inertia. Head will be whiplashed backwards in this case. Even more interesting phenomena here is that the head itself is obliged to the torque. Yeah, the torque is a measure of force that can cause an object to rotate. Head starts to rotate at this moment as well. And this is also a little bit tricky moment here. Rotation of the head. This is one kind of whiplash when the head is uh, pulled backwards. But then there's collisions where the opposite is happening. If the driver sits in the seat and the car is hitting the wall, think about the head. What happens with the head? Seat belt tries the body to be, well, in the seat, but the head will be moving forwards and will get other type of whiplash. There are two different whiplashes, backward and forward whiplashes with a little bit more precise name. And torque. Torque, we will return back to torque shortly, but as I said, torque is a one way how to measure the force to start or to stop the rotation. Start or stop, let's say to change the amount of rotation. Sudden change of velocity can be related also with a sudden change of momentum. Is it possible to die if you jump out of the airplane without the parachute? It depends. It depends how long it will take for the parachute jumper to slow down. It is not actually the final speed that is killing you. It is actually in rapid change of velocity. So if we look here on this schematics, here is triangles, difference of the velocity and difference of the time. If we have fast speed and when you hit the ground the speed is 0, and if that happens in the relatively short time, it means that large number is going to be divided by small number, and the result is supposed to be large. But if the time difference is increased, then that means that large number is divided by a large number, and the result is small. Yeah. If we take this division and multiply it with the mass, we actually get what we are familiar with a force. So let's watch this small tiny video and check this out. Two helpers are jumping along. Let's move it a little bit more forward, where the things get interesting. Because of air friction, the velocity is constant. No, relatively constant. It depends on how the jumpers are holding their arms, controlling the speed. They can dive, they can stretch their arms, and then they get maximum surface area to the air. Yeah, and it's still possible for them to change the speed in such a way. And this is the moment when the things could get deadly. He is aiming. You can actually see how he is aiming to the net, and when he will hit the net, uh, we can think about how much time it's gonna take. Yeah, GoPro. Yeah, it took a pretty long time to slow him down, and because this time is relatively long, this is the reason why he is surviving. He didn't get so much so-called force, average force in this moment um, for this collision. And yeah, thank you. So if we look on this formula a little bit more, we can actually multiply. We can multiply mass with the velocity, with two velocities, and think about something which is called momentum. Momentum is mass in motion. And once more, sudden change of momentum uh, is the reason why the force is deadly at this previous example. Here in this example, here in this example, we can see something similar with some extras. Yeah? When the person is falling on the net, net is slowing the person down, but net is also moving down with a certain initial velocity, with a certain start velocity. But because of the elasticity of the net, well, the net is elastic and pulls back the person. But check out the leaves. Leaves at the moment when the person is hitting the net are stationary, of course, because they are at that particular height having zero speed at the moment when the person hits the net. But net, on the moment when it got hit by the person, the initial speed is equal to that person's initial speed. Yeah. So think about what is the initial speed of the leaf right now, and what is the initial speed of net of that particular moment. Yeah, momentum. A few famous Newton's laws of motion, three Newton's laws of motion. First of all is law of inertia. I can give you the Latin version of it and a few unofficial versions of it. If you want to find the real physics version, check out what Webster Dictionary is defining the first Newton's law. But for us to understand is this: whatever is in a motion will stay in this motion unless something from a side will affect this motion. If you think about a car driving on the street, what could be affecting this car? Air. Firstly, that's air, what comes in my mind, because air molecules are colliding with a car which is driving. And the second part is a friction on the wheels, on the tires. This friction Yeah, if it would not exist, well, yeah, then this motion would be more efficient, I could say. Yeah, but then this problem would be to, well, slow down. Yeah. Think about the satellites in the space. They gain its speed, and then they are in the orbit with that speed, and they do not have any engines turned on constantly to maintain this velocity, this speed. Velocity and speed is similar concepts here. Satellites don't have any friction acting on them. No, well, relatively speaking. Yeah. There are no air which could slow the satellites down. Maybe some cosmic dust, but well, I am not mentioning them right now. And those satellites will always be in motion. The same about the rotating objects. Think about something which rotates. Wheel. Um, how long wheel will rotate? Well, it depends. It depends of how oily that part of the wheel is, axis of the wheel. If it has a lot of oil, that means there's a small friction and the wheel will rotate longer. And of course, air resistance also is important here. So as long as there's nothing which could affect the motion, this motion will maintain its velocity or angular velocity, linear or angular velocity. Linear velocity for the linear motion, angular velocity for rotational motion. Newton's laws of motion, the second one, is where the measure, which we are know as a force, is defined. And it comes from actually acceleration. If we apply force on something which has a mass, and the force is all the time the same, but one object has small mass, another object has large mass, what do we achieve is we achieve different acceleration. This could be seen from that point of view that if the mass is constant, more force will give more acceleration. Remember that acceleration is change of the velocity, change of the speed. Yeah? More rapid speed is changing, more acceleration the object or whatever is having here. Yeah. So all these phenomena, putting this together, gives us this most famous formula in the physics, which also is most familiar in this form, that where the force equals when you multiply mass and acceleration. The original notation of this formula would be where you are looking on what would acceleration, how it would be related with the force and mass. So let's say that original force, acceleration is what we are looking for, and looking how the acceleration is changing. So what I need is let's say force over mass. And we clearly see proportionality, direct proportionality with the acceleration and force, and inverse proportionality with the acceleration and mass. And we know that the units are newtons. What newtons are made of? Kilograms because of the mass, and acceleration because meters per second in each second. A little bit of how meters per second are becoming in this form for acceleration, units for acceleration, is that the acceleration itself is supposed to be change of velocity in time. So what I see here is velocity, and velocity in the term of units is meters per second, over second. So because of those two division lines, I can simplify it like that. Let's say that I'm rewriting that meters per second divided by second. And because we should not write these division points like that, I can rewrite it as a multiplication. This is meters per second times 1 over second. And this makes sense. Now I can multiply m times 1 second by second, and what I get is meters per second squared. Remember these in the square brackets, yeah, these are units. And this part here is a physical relationship formula. 3 physical formulas, and the rest of these in squarish brackets, those are units. So that's about a little bit of math behind of acceleration. And yeah, for rotation, we could say that if we want to increase the speed of the rotation, if we want the thing to spin faster, we need to apply force. But at this moment, we need to apply force at certain distance, and the force together with the distance is called torque. And then there's a third law of the motion, action-reaction law, also one of the most important cause for traumas. And what I see here is these 3 statements, where each next statement is relying on previous one. Every action has its reaction. Yes, true. Indeed, it is. Very often, not only in the physics, but also in society too. Every action has its own equal reaction. Yeah, equal and opposite reaction. Well, that's what you definitely see in the animation. And there's more. There's also this animation here. Well, if you are shooting with the rifle, hold it steady, because you're gonna get recoil. There is an action and reaction, recoil. This is also the answer to the question, does the Earth attract you? And the question is, yes, it attracts you as well, and with the same force how you attract the Earth. I meant it all other way around. Do you attract the Earth? Yes, you indeed attract the Earth. Yep. Well, I am trying to do my best by giving this lecture as in a one go. This statement that centripetal force is an opposite force to centrifugal force is not entirely valid, because we have to remember what is the frame of reference frame, inertial reference frames or non-inertial reference frames. About those, probably you will get some clarified information during the course. And yeah, one more example here is about holding rope. Hold the rope, I pull it, you will pull it, and it turns out that if the rope is not slipping out and we are holding it, not moving anywhere, rope has its tension on it, and my pulling force is equal to your holding force, and it is also equal to the rope's tension force. Everywhere in between, if you're gonna put some dynamometer, let's say this is the rope, this is one of the person holding it, and this is another person holding it, yeah, and you are pulling it in that direction, and somebody is pulling it in this direction, and you start to measure with how much force, this force and that force, this is going to be equal force. And if you will attach some kind of dynamometer and measure how much force is here, it's going to be exactly the same force. Only thing what's going to be different is direction of the force. Direction of this force, if we associate this force with a person or with a rope. I will leave this to think about that. What is the direction of force and how this is related with the persons and with the rope. Pulling force, holding force, tension force. 3 different ideas here for you to think about this. But I will move on. Force and energy. It turns out that, well, you can exert force. You can apply the force um, with your hand because, well, if you have to lift some objects, you are doing that. You are exerting force. But from where this force comes from? Well, from energy. What is energy is a tough question. My favorite answer to this question is that energy is ability to perform work. And to perform work, for the work, we will need a force. Energy in the human body, sources, like consumption, food, also heat. Yeah, if it's too cold, well, we're gonna die because of our body needs to maintain homeostasis. Um, sun, no, well, it's tricky. It's depressing to live where there's a lack of sunlight. But yeah, for eyesight, sunlight brings the energy, and we are able to see because of the sun. If it's a really a source as the source, I think about this sun example as really thinking out of the box for this given example. We can live without the sun during night, of course. Yeah. Storing the energy. Yes, well, we have our own temperature maintained by homeostasis, and we can, of course, store it in the particular type of tissue, fat tissue, muscles. And the last part here is how we're going to spend the energy in a few ways. Is, of course, we can do work, we can perform mechanical work using it through the mechanical energy. We can look through to ourselves through the thermal imaging camera with the infrared camera, and we will see that we are glowing. Remember that previous example there. Infrared. This is how we are glowing. We are glowing in the infrared. And of course, we can give out the energy in the form of heat. Hold somebody, and you will feel that this heat from you is transferred to the somebody, or well, the second thermodynamic law says that heat transfer happens from the system with a higher temperature to the system with a lower temperature. The more hotter person will warm up more colder person. Heat transfer will be where your or your partner's energy is gonna get spent. If we look on the mechanical ideas here, the next thing I'd like to discuss is liver system. Musculoskeletal system is a complex liver system, and livers have three different ideas because there are three ways how we can build a liver. First of all, that's the balance. First type of the liver to balance things. And I have one example here from the physiological point of view, and this is the head. The resistance, the applied force, and the fulcrum are three parts which we can combine spatially where we want. And you see that resistance is what is, well, let's say, going downwards. So yeah, and we need to maintain the balance with help of the muscles, applied force, with the help of, as I said, muscles. A fulcrum is the backbone, actually. Yeah, all of the system is balancing on the backbone. So that's the type of the liver. Then we also can see the second type of livers, and this is related with the work. That's why there's a work formula jumping out, that with the help of the liver we can reduce force what is needed to perform a work. I think this schematics is really familiar for those who have been working in some summer jobs or in the garden or in the construction. If you have longer handle, you can apply less force to move or lift your resistance, or in this schematics, this is called load. Applied force is effort, and the resistance is load in this schematics. Well, longer the bar is gonna be, more easier, less force you will need to use to pull up the load. This we also can find in the human body. And think about feet. Think about the feet. Where's the fulcrum? It's your finger toes, tip toes, fingers of your feet. And then there's a muscle behind of the tibia, and this muscle is pulling upwards tibia and everything else, and staying stable. Well, being stable, that's another topic, but lifting human body on the fulcrum, which is, as I said, this finger toes. Force, applied force, is this muscle in the end of the drawing. Load is actually equal to the weight, what we need to lift up, and fulcrum is this part. Yes, in all different schematics, we can use different notations, as you see here, but keep in mind that as long as you follow the ideas what's drawing here, it's all the same. And then the third one is to increase speed, what is needed to perform the work. And the story is that we are just reorganizing the lever system. That firstly we have axis fulcrum. If I am adding something to this image, then I should draw fulcrum here. Then the resistance or load is in the end. Previously it was before here. And the force, applied force or effort, also called effort, from previous drawings, also here, is in between. And that's what we definitely see here. The axis and fulcrum is this part. Applied force is here, and the resistance which we want to lift up or load is obviously in our palm. And at this moment, what we want to achieve is speed of this part, and we are sacrificing force. So if we need to lift something what weighs 1 kilogram in your hand, and we are applying force here, then this is definitely way more than 1 kilogram or 10 newtons, greater than 10 newtons. No, it's other way around. Sorry. The force is definitely greater than 10 newtons. Remember that 1 kilo is roughly 10 newtons. The force we are applying here upwards, because of it's really close to the fulcrum or axis, is way more than 10 newtons. Okay. What else I have here is mathematics behind of the levers. So the ratio between the resistance force and effort force, or effort distance and resistance distance, it can be really easily seen here in this first type lever. And this can be calculated. How it's usable, or how we can apply it. Well, solving exercises like these ones, remembering this ratio, then reorganizing ratio in this equation, then reading that, well, what is the mass, and the mass actually is hiding in the weight of the rock, and weight is equals mass multiplied by freefall gravity acceleration, which we already know is 9.81. And then this final formula which we need to solve is slowly getting in this form. What we see is we start with the ratio for mechanical advantage. We know that ratio is always the same. We reorganize ratio like that, and we get a second formula equation. Then we find out that, well, we have to know mass, and mass probably hides in one of the force, and it hides in the form of weight, and that means that mass multiplied by gravity free fall acceleration is actually weight. And now we go to the last stage, where we are plugging this m of the rock times g inside here, getting the formula number 4, mg. So this is the new F2. And what we need is we need to bring GD on the other side of the equation. And that means the GD here, it is in the upper part of the division. Here it goes on the lower part of the division. Well, mirroring the equation, this is the final form what we get. Plug the numbers in, and what do you get is the weight of the rock. So plugging in numbers, solving that, well, the rock weighs 30.6 kilos, roughly speaking. How this is relevant in medicine? Well, and one example from the dentistry. Dentists, well, firstly, they drill crown removal procedure. This is what it is called. Crown removal procedure, removing crowns. Crown. So if there's a crown which needs to be removed because it is having some glue on it, on this what's left of the teeth, first of all, we just drill part how to access the underneath of the crown, and then we use this flat tool and rotate it sideways, and then the crown comes off. Why not? Really nice way how to deal with the lowers in the dentistry. Well, levers and first type levers are related with the balance and making things stable, or how this is called in Latvian, in English, stability, statics. Yeah, statics, statics. These questions: where's the center of the mass? Well, it depends what is your form. If you are sitting right now, could the center of the mass be a virtual point outside of your body? And the answer is indeed, it could be. Think about that. Lean, stay on your legs and lean forwards. Stay on your legs and lean forwards. So think about where is the center of your gravity, center of mass. It's a little bit out of your human body as a virtual point. How to achieve stability is Well, we need a base support, and we need to know where the center of the gravity is. The image is in the 2 dimensions, but in reality, we have to remember the 3rd dimension also matters. And as long as center of the gravity is within the uh, area of the base support, the uh, object is in balance. If there's no balance, then, well, things tend to fall apart, and we could think about rotation. If the lever is not in a balance, sorry, yeah, then the lever will start to rotate. So the Garfield has its weight, and Garfield is staying particular distance away from the fulcrum, and the rotation will start to happen. This is where we return back to the word torque. Torque is the multiplication of the force and the distance. So everything which rotates, even the previous example of lifting the crown from the tooth, when the instrument is rotated, the person, the dentist, is applying the torque. He is starting the rotation with his force. Yeah, but this force, because of this instrument has its certain size, multiplied by the radius of this or the distance to the rotational axis, will describe the torque of this instrument. Think about this. If the Garfield is staying closer to the middle point, closer to the axis of the rotation will still start to happen, but the speed of the rotation, the acceleration of the rotation, yeah, angular velocity changes will not be so great. Angular velocity will be increased, but with a slower rate. So it actually significantly matters how far Garfield is staying away from the axis of rotation. The last case here would be that Garfield is staying exactly on the fulcrum, exactly on the axis of the rotation, on this reddish line here. Will the bar start to rotate? Well, no, because the distance is equal to the 0, and anything multiplied by 0 is 0. Yeah. If the Garfield stays way farther away in this lever, the torque will be greater. Interesting moment here is that torque is also called moment. Both of those are measured in Newton meters, and I don't have a clear answer why there are 2 words of this. How to stop rotation? Well, we will need to apply some force to stop the things which are rotating. Will this particular situation with the Garfield will it stop by itself? No, yes, because if we think about the cause of the rotation is weight of the Garfield, the rotation won't do the full circles here. It will probably gonna go to the other side, and because of the friction won't reach the equilibrium point, and the oscillations will start, and then of course the rotation will end when the beam or the bar here will be in horizontal. Instead of horizontal, it will be vertical direction. But of course, that's not going to happen with this case, with the Garfield staying on it, probably because of he will lose its stability and will fall off from the bar. This is the moment where, interesting, pun intended, moment of inertia is a measure of object to be in a motion, but in rotational motion. The best way how to think about this is in analogies. So if I have a an object with a mass, and mass is object has a lot of mass. This object has a lot of inertia. If we look on this in the rotational motion, then everything which rotates has its rotational inertia. And this rotational inertia, interestingly, it depends of the shape. Yeah. If we look on this animation, then the last part where I have two bars, the final formula for how much inertia for rotation the object is, well, it depends of where the rotational axis is, what is the shape of what's rotating. It's actually dependent on distribution of the mass which are rotating away from the rotational axis. That first image, rotating teapot, teapot, there's a sigma sign in it. Sigma means the sum of all points, all molecules, all atoms, multiplied by how far away those atoms are from the rotational axis. If we, and this need to be squared. And if we know this value, then obviously we add those values together, and these multiplied values together, and then we get what we call inertia, moment of inertia. How these formulas are obtained, integrals helpfully for us, allow us to do that. But let's return back to the torque. Last part, or last slide about the torque is that torque also has its analogy. Torque is analog to the force. Torque is how much rotation can be changed if I apply some force. How much motion can be changed. Because when you have the torque, you do exactly the same thing what you do with the force. With the force, you change the velocity. With the force, you accelerate. You increase or decrease the velocity. With the force, you can make things to happen move faster, or you can make things to happen move slower. That's what you do with the force. What you do with torque is you change its angular velocity, and torque has its torque hides the force in it. In this moment, we can see that the torque, which is also a moment, can be found from another formula. If you know the angular acceleration and you multiply it by momentum of inertia. Pay attention to the analogy with the both formulas here pointed out. Force, which changes the motion, and torque or moment, which is also changing the motion. Here it changes linear motion. Here it changes rotational motion. In the force formula, we have the acceleration, but linear acceleration, which is the change of velocity, how much velocity is going to be changing. Remember that, well, acceleration is, I already draw, change of velocity in time. Here, this epsilon here is a angular acceleration. It also is acceleration. Epsilon in this moment is angular velocity, and angular velocity we draw with a small W looking Greek symbol, which is actually omega over, and a change of omega over time. So epsilon acceleration is how fast rotation, angular velocity, is changing in time. If it rotates slow and then in a really short time it rotates fast, then angular acceleration is high, a lot of acceleration. And the last part is a moment of inertia. Capital I, what we saw in the previous slide, is handling mass. and how far this mass is from rotational axis. And we look on all points. That's why I have sum of all points multiplying mass with the how far they are from the axis squared. That's what inertia is. But we also have mass in the linear motion as well. So mass and inertia of the mass, both of those are fundamentals of describing motion. In one case, linear motion, in another case, rotational motion. There's a lot of analogies which you are supposed to see here. Okay. Angular momentum. Impulse. Now, yeah. Sometimes some literature is writing this with an impulse, sometimes it's writing in a momentum. And I'd like to use, yeah, impulse is something else. Delete this word here, yeah, and instead of impulse, we are supposed to write momentum, linear momentum. Yeah, this is my mistake. But, well, things like that happen. Yeah. So momentum is when we know that there's something which moves with certain velocity. And if we multiply mass with a velocity together, we get what we say that's momentum. Remember this formula where we had F multiplied by change of time equals change of momentum. Yeah. And if we start to analyze this equation here out, then it's actually mass change of velocity. Yeah, well, that's how it's gonna be written. Mass multiplied by change of velocity. Yeah, mass is constant, velocity is changing. That means that mass can be brought out of the momentum based on this formula here. Yeah. And this seems familiar to what you saw some 40 minutes ago on one of those slides. And momentum is conserved. In the collisions, momentum is conserved, but the, well, energy can be converted to the heat most often in the reality, in the real life. And this conserved momentum can be thought as amount of motion. If we have linear motion, we have the amount of, well, something which is moving linearly, amount of it. If we have something rotationally, then we definitely see that there's amount of motion, but in rotation idea motion. So here analogy is that, again, we have moment of inertia, this one, and I'm drawing it again. This is where the mass can be found, multiplied by how far these points which have mass is from the distance of the rotation, and then we add all those points together, and we have something familiar from the last slide, omega, which is how fast a rotational object is actually moving. So multiplying these two things, we get so-called angular momentum. And as angular momentum is conserved, this can be seen also in one of next slides here, that if one parameter goes up, the other parameter has to go down. Amount of rotation is conserved and the product has to be constant. Okay. Amount of the motion is constant. So if there's a small angular velocity, that probably says something about the moment of inertia, it's high, and vice versa. Where this can be seen is in the life is ice skaters. They are in a motion, and the motion of the rotation is relatively slow when the hands are stretched out. Hands are stretched out. That means that the molecules, cells, everything her body consists of has a lot of distance from the rotational axis uh, to those uh, cells. Yeah, and if she is changing the distance, and she can do that because she is pulling her hands closer to her body, she is decreasing the moment of inertia. So if moment of inertia goes down, that means that this angular velocity has to go up. She is changing moment of inertia by pulling hands closer, but physics is doing something with angular velocity, is increasing her rotational speed. A little bit about the flows. Uh, if we think about what is flowing, then and how it is flowing, then we have to understand types, speed. There's also some kind of pressure involved. Yeah, and what exactly is flowing. Fluids and liquids, what's the difference? Well, gases also are fluids. Everything what can flow is defined as a fluid, but liquids are a state of the matter. So if we think about what exactly is flowing, fluids which have viscosity could also be thought as the fluids which have resistance to flow, and everything has a resistance to flow. This resistance can be constant, and then we say it's Newtonian fluids um, without any admixtures like blood plasma, or we could have so-called fluids with a non-constant resistance to flow, and that's blood. How to say? If blood have its cells, we can think about these blood cells are with different effects affecting the blood flow and making the blood at one moment flow better and at some other moment flow not so good. For example, this example with the cornstarch. Yeah. It's just an admixture, cornstarch used in a kitchen in the food industry, added to the water. And because those admixtures cannot escape so easily from one from to another, these cornstarch starts to act like a solid. And if you are fast enough, you can run on the surface of the cornstarch dissolved in the water. Particles cannot escape below of this feet, and yeah, that person is able to run over the liquid. Types of the flows is represented with the two types. Here we can find laminar and turbulent flows, and how to distinguish and how to measure with the help of how fast the flow is, what it consists of, what is its viscosity, how huge the diameter where it is flowing is, and that's the Reynolds number. But about that you will have a specific class. Next thing is about the energy in the flow. If something is flowing, there is a energy in this flow, and energy has to be well, kinetic because fluid is moving in the flow. Yeah. And one more thing here is interesting is there's a pressure, and there are at least 3 different type of pressures we can discuss static pressure, dynamic pressure, and total pressure. Total pressure is the combination of static and dynamic. Static pressure is this pressure to the walls because of this fluid motion, and dynamic pressure is pressure in front of the in the flow. And here this schematics say what happens with the velocity, and at the same time we have to think about what will happen with the pressure. So here, where the tube is wide, we have laminar flow and the velocity is relatively slow. Here, where there is a narrowing, the idea is that velocity has to increase because of the continuity. Same amount of water which is here in this cross section has to go through at the same time here. So the velocity has to go up if the space is smaller. So velocity goes up here. Then velocity decreases somewhere here. Well, I'm not sure this is correct drawing here, but roughly speaking, we could think about that. And somewhere here, the flow becomes, after the narrowing part, flow becomes turbulent, and the speed is varying a lot. And then, of course, it becomes more laminar again, and the velocity stays more or less the same as here. How about the pressure? Pressure is interesting. We know that there are two types of energy, kinetic and potential energy. I didn't explain them too much, but the idea is that energy is also conserved. If I have particular amount of energy in the wider part of the tube, this same amount of energy has to be found also in this narrowing part of tube. That's why I need in the next slide. Yeah, so the total energy is the sum of kinetic and potential energy. It has to be constant, and let's go to this slide. Similar diagram where I see that same tube, which is wide here, becomes narrow in the middle, and then it becomes again wide over there. Turbulence is taken out of this schematics, but let's look on the total energy. Total energy everywhere has to be constant. In the wider part, it has to be constant, let's say 10 units. In the narrower part, it has to be constant 10 units. Here, after the narrowing part, it also has to be constant 10 units. And total energy is sum of energy of the speed, so that's the blue line, blue line, and sum of the pressure. So if I take energy from the speed, which is slow speed, so small energy in the white part, it has to be that the energy from the pressure is larger here. Well, when the tube gets narrower, it's other way around. Speed gets higher and the energy from the pressure is lower. It doesn't make sense when you start to, well, look at this and think about leak. Well, come on, it should be that where the narrow part is, then there's supposed to be higher leak, but it's not entirely true, because we have to understand this is a whole, the constant system with a total energy being constant everywhere. And think from the molecular point of view. If you have constant total energy everywhere in every part of the circuit tube system, then here where the speed is slow, molecules are busy with the pressing on the walls. Molecules are using most of the energy to the exert pressure on the walls. Here, where the tube gets narrower, molecules are busy to run, to achieve speed, so they don't have time to press on the walls. Remember, total energy is constant. If it's not constant, then of course that's totally different situation. Yeah. So this is how we have to understand the Bernoulli's law. conceptually here. Where it shows up in the human body. Well, in flatulence, if you know what flatulence is, another word for it is letting out the gas of the intestines. Yeah. If I take 2 sheets of paper, and that's what you can do that right now, take 2 sheets of paper, hold them in your hands like this. So one hand is picking one sheet here, that's your hand, and this is you. Another hand is holding paper, sheet of paper, like that, okay? What you have to do right now is imagine what happens if you blow some air. Let's change the color for this. If you blow some air through those sheet of paper, what will happen with a sheet of paper? Think about that firstly. Will they come together? Will they spread apart? Or nothing's going to happen with this 2 sheets of paper? If you want, you can check it out. Interesting is, yeah, this homepage here, you can find more physics than what I'm drawing right now about flatulence or letting gases out of the intestines. The answer here, if you haven't tried it, is the sheet of paper will come together. They will tend to go together. And why it is because of this Bernoulli's law and pressure. While there is no airflow, the sheet of paper are standing still, and the air pressure from both sides, from outside and also from the inside, is the same. But because here in the middle, now we have airflow happening. Yeah, this is what happens between the sheet of paper, airflow, flow. The pressure inside is getting smaller. So this becomes smaller. Yeah, this is smaller, outside is larger. The same happens on the other side of the sheet. This is outside pressure, this is inside pressure. So where the pressure is more, that pressure will win. And those 2 sheets of paper will come together because outside pressure is greater than inside pressure. Airflow, air molecules are busy with running through that 2 sheets of paper, and those two sheets of paper will come together. So last part here about the flatulence is that there's a particular type of sound during this procedure. We usually refer it to the fart. Yeah, that's what it is. And how the sound is produced? Well, the answer is we have the gas inside of the intestines, which are going through the sphincter muscle, which are represented by these 2 sheets of paper. And when there's a first portion of the gas going through the sphincter, sphincter has inside pressure low, outside pressure high, sphincter goes close together. But we have a lot of portion of the gases inside of the intestines, and pressure builds up behind of the sphincter, and the next portion of the gas is breaking out through the sphincter, and this sphincter is again widening up because of this gas pressure, and the next portion of the gas goes out. But because we have next portion of the gas and there's a velocity, so that means that the inside pressure decreases, outside pressure increases, is greater than inside pressure, and the sphincter goes closed again. And this happens roughly hundreds to 300 times per second. That's the physics behind flatulence. A little bit more you can find on this website. Let's remove that person. Blood pressure. Yeah, here in this diagram, you see that the pressure is also related with the flow, as I previously said, and the highest pressure is in the arteries. In the veins, we have the smallest pressure because all of this resistance, what blood vessels are having, is already decreasing this blood pressure. How much blood can push more farther away from the heart, this less it is able to push. Resistance is decreasing this blood pressure. Pascal's principle. This is similar to the levers. Pressure is equal everywhere in an enclosed system, and with a small force acting on a small area, I can gain a lot of force acting on a lot of area, and this is coming from the pressure definition. So if pressure is defined as the force acting on the area, then force is pressure multiplied by area. And if area is increased, force also has to go up. So if I am taking small force acting on small area, I'm going to get large force on large area, keeping the pressure constant. Pascal's principle is pressure is constant everywhere, and that's the answer on this question. This seems familiar. This sounds like a mechanical advantage, a little bit reorganized fraction here, but mechanical advantage, or Pascal's principle in hydraulics reminds me, and probably for you as well, levers. And that's the answer why the eye hurts if you press on cornea. Yeah. The pressure on this cornea, yeah, well, don't do any damage on the cornea itself, but because the rest of the eye also has its area, this small pressure is transmitted through the fluid, because we have the fluid inside of the eye, and this force on the rest of the area is getting that pressure, which is coming from the when you press on the cornea. So a little bit push on the cornea is actually doing a lot of damage on the rest of the eye. So please avoid pressing on corneas, even in, I don't know, fighting. Yeah. We are approaching the last part of the lecture, and this is related with the resistance to flow. Poiseuille's law is talking about two things. It depends on how you look on the formula: resistance to flow or blood flow rate. Yeah. The story is about two different sides of the vessels. You could have narrow vessel and twice larger vessel. Let's say that vessel number 2 is twice larger than vessel number 1. So if the vessel is twice larger, it has less resistance for blood or any kind of liquid to flow. Or in other words, for the same amount of energy, we can get more liquid through that second vessel. Think about syringes. If you have tiny needle for the syringe, it's hard to push. If you have a syringe with a wide needle, it's way more easier to push the liquid through it. Think about the way, how do you push it? Hold the feeling the same when you push the liquid, and you will find out that in one case, you will get just a little bit of liquid out of the needle in 1 second. And in the second case, where the needle is way more larger, with the same push, same feeling of the push, you will get, okay, how many times more liquid out of it? And these formulas are technically saying the same thing. Either for the same push, you're gonna get 16 times more flow rate out of the twice larger um, vessel. Or the first idea says that it's going to be 16 times harder to push if the blood vessel is twice smaller, or 16 times easier to push if the vessel is twice larger. It doesn't matter the direction. That's what the formulas say. That's the proportionality here. Poiseuille's law talks about both resistance to flow or blood flow rate. Few things about weightlessness effects on the humans is returning back to the gravity. Yeah, short-term vestibular system failure, long-term fear of biochemical related stuff here. Loss of muscle mass, change of body size. We usually live in a gravitationally environment where gravity exists, let's say like that. Yeah? And our body is used to that, and heart work, the work what heart is doing is used to pump the blood from the lower part of the body to the back to the heart. If we don't have any gravity, then there's no need to do so much work, and the body is getting lazy. Muscles are getting lazy. Related ideas here with a physiology is that, okay, if we have too much pressure on the upper part of the body because of fluids shifting, then, well, we could have something with ophthalmology related things. Increased eye pressure, and that's dangerous. There's more under this website. It depends if you want to read more about these topics. I strongly encourage you to do that. And this topic, what's going to be in these last few slides, is related with a second semester lecture, and probably I will, or my colleagues will give you second part of this lecture about the electromagnetic force, about nuclear force, about radioactivity, and everything else. Thank you for your participation, which is pretty weird to say because this is video lecture. I hope that the stories were entertaining enough for you, and that something's valuable is what you got out of this lecture. Thank you.